June 6, 1944. The largest amphibious invasion in human history has just begun. 150,000 men are crossing the English Channel. 5,000 ships are on the water. The beaches of Normandy are being stormed. Everything the Allied war planners have built toward for 2 years is unfolding exactly as designed, and the men on those beaches are fighting and dying to make it work. But here is the thing nobody talks about when they talk about D-Day. Landing on the beach was only the beginning of the problem. The harder problem, the one that kept the planners awake for months before the first soldier ever set foot on French soil, was what happened the day after the landing, and the week after, and the month after. Because 150,000 men need to eat, they need ammunition, they need fuel for their tanks and vehicles, they need replacement parts, medical supplies, artillery shells, reinforcements, and the continuous logistical support of an industrial civilization that is now fighting a war on the far side of an ocean and a channel. You cannot bring all of that across a beach. You need a port, a real working port, with deep water berths, cranes, warehouses, pier heads, and the infrastructure to unload thousands of tons of cargo every single day. There was no port, not a usable one, not where the Allies were landing. The Germans knew this. The German General Staff had studied the problem with the same rigor the Allies had. Their conclusion was categorical. No major amphibious invasion could be sustained without capturing a major port within days of landing. If the Allies landed somewhere without an accessible port, their invasion would fail from supply starvation even if the initial assault succeeded. The men would be on the beach, but the war machine behind them could not follow. So the Allies built 2 ports, in secret, in England, in pieces small enough to tow across the channel. They built them in 8 months with 20,000 workers, 2 million tons of steel and concrete, and an idea so operationally absurd that when it was first proposed in a military conference room in 1942, the senior officers present responded with hoots and jeers. The man who proposed it was Lord Mountbatten. The idea was this: if there are no ports where we need them, we will build ports and bring them with us. Stay with me, because what the Allies actually built, how they built it, and what happened when the English Channel tried to destroy it, is one of the most extraordinary engineering and logistical stories of the entire war, and almost nobody knows it. To understand why the Mulberry Harbors existed, you need to understand the fundamental problem that every amphibious invasion in the history of warfare had faced, and why, by 1942, that problem had become the central question of the entire Allied strategic planning process. An army on a beach is an army in a temporary position. It has to move inland. It has to fight. It has to grow. And to do any of those things, it needs a continuous supply line connecting it to the industrial capacity behind it. Every division in active operation, the Allied planners had calculated from their experience in the Mediterranean, consumed between 600 and 700 tons of supplies every single day, not per week, per day. Ammunition, fuel, food, medical supplies, replacement equipment, everything that keeps men alive and fighting. 600 tons per division per day, multiplied by the number of divisions the Allies intended to put ashore in France, produced a number that was staggering. And that number had to arrive on those beaches every single day, without fail, regardless of weather, enemy action, or the mechanical reliability of the supply chain. Before the Second World War, the doctrine governing amphibious operations was unambiguous on this point. A major amphibious assault had to capture a major port within days of landing. If it could not, the invasion would fail. Not might fail, would fail. The logistics could not be sustained across open beaches. Open beaches meant dependence on flat-bottomed landing craft that could not operate in anything but relatively calm conditions. Open beaches meant no cranes, no deep-water berths, no capacity for the heavy equipment and bulk cargo that sustained modern military operations. Open beaches were, by the pre-war consensus of every naval and military planning establishment in the world, a temporary measure that led to a permanent port or led to defeat. Eisenhower understood this completely. He had studied amphibious operations with the seriousness of a man who intended to execute the largest one in history. He knew that the capture of the port of Cherbourg, the major facility on the Cotentin Peninsula, the one the Allied planners hoped to reach by D+17, was not just a tactical objective. It was the logistical foundation of everything that came after the initial landing. Without Cherbourg, or something that functioned like Cherbourg, the invasion could not be sustained into the deep offensive operations that would actually win the war. But Eisenhower also knew something that complicated this dependency in a very serious way. The Germans knew it too. They had read the same doctrine. They had studied the same problem. And their response to the Allied invasion, when it came, would include the systematic destruction of every port facility the retreating Wehrmacht could reach. If the Germans could deny the Allies the use of Cherbourg's port infrastructure, by sabotage, by demolition, by making the port militarily unusable before surrendering it, then the logistical foundation of the invasion could be undermined even after the tactical objective had been achieved. Cherbourg finally fell to Allied forces on June 27, 1944, 21 days after D-Day. The Germans had used every one of those days. The harbor had been mined. The cranes had been destroyed. The dock facilities had been systematically demolished. The port that Allied planners had counted on as the critical supply node for the Normandy campaign was, at the moment of its capture, almost completely unusable. It would take weeks of engineering work to restore even partial functionality. Eisenhower had known this was a likely outcome. He had planned for it. The plan was the Mulberry Harbor, and the Mulberry Harbor had begun as an idea so unconventional that the people in the room when it was first proposed did not take it seriously. Spring 1942, a conference of Allied service chiefs in London. Lord Louis Mountbatten, Chief of Combined Operations, proposes a solution to the port problem that no one in the room has heard before. If adequate ports are not available at the invasion site, he says, we will construct artificial ports in pieces in England and tow them across the Channel to France. We will build the harbor and bring it with us. The room responds with laughter, with dismissal, with the institutional skepticism of professional military officers confronting an idea that violates the categories of what they consider achievable. Building a major port takes years. It requires geological surveys, foundation engineering, the movement of enormous quantities of material in a controlled environment. The idea of constructing a functional harbor in Britain, dismantling it into towable pieces, moving those pieces across one of the most treacherous stretches of water in the world, and reassembling them on a hostile frantic coastline under enemy fire, this was not engineering. This was fantasy. 2 years later, that fantasy was sitting on the floor of the English Channel off the coast of Normandy, and an LSD was driving its ramp onto an artificial pier head and unloading tanks directly onto French soil. The journey from the laughter in that 1942 conference room to the working harbor off Normandy in 1944 is one of the most remarkable stories in the history of military engineering, and it begins with a very clear-eyed understanding of exactly how difficult the problem actually was. Most people who have not worked on the water think of the English Channel as simply a stretch of sea between Britain and France, a geographic gap that needs to be crossed. 22 miles at its narrowest point, 100 miles or so where the Allies would be crossing to Normandy. An obstacle, certainly, but not a fundamentally different problem from any other body of water. The engineers and naval officers who had to plan the Mulberry operation knew the Channel was something else entirely. It was one of the most technically hostile bodies of water for engineering work in the world. And understanding why explains both why the Mulberry harbors were so difficult to build and why the storm that nearly destroyed them in June 1944 was able to do what it did. The tides on the Normandy coast are extraordinary. The difference between high tide and low tide reaches more than 21 feet. 21 vertical feet of water, twice a day, every day. At low tide on the flat Norman beaches, the waterline retreats a quarter of a mile from where it was at high tide, a quarter of a mile of bare sand appearing and disappearing twice in every 24 hours. What was sea bottom in the morning is dry ground by afternoon. What was dry ground becomes sea floor again by evening. For a fixed engineering structure, a conventional pier, a normal breakwater, a standard dock, this tidal range is essentially impossible to accommodate. A pier built at the height appropriate for high tide would sit 21 feet above a vessel's deck at low tide. A vessel trying to use it would find its ramp unable to reach the pier surface. A pier built for low tide would be submerged at high water. The engineering of conventional port infrastructure assumes a relatively stable sea level. The Normandy coast had nothing of the kind. Then there were the currents. The English Channel is not a calm body of water with tides moving gently in and out. The tidal flow drives enormous volumes of seawater through a relatively narrow passage with tremendous force, alternating rivers running east and west along the coastline every 6 hours as the tides ebb and flood. These currents were strong enough to make the handling of vessels on or near the beach a constant navigational challenge even for experienced seamen. For large, slow-moving engineering components being towed into position, they were a serious operational hazard. And then there was the weather. The English Channel is subject to violent storms at all times of the year. Gale-force winds, heavy surf, the full sweep of Atlantic weather systems pushing down through the channel with nothing to break them before they reached the Normandy coast. The coastline where the Allies intended to land offered no natural protection, no sheltering headlands. No offshore islands creating calm water in their lee. The beaches were fully exposed to whatever the channel chose to deliver. It was that very hostility, the same storms that had broken the Spanish Armada in 1588 and frustrated Napoleon's invasion plans and given Hitler pause about crossing to England, that had convinced the German general staff that a sustained supply operation on the open Normandy coast was militarily impossible. They were right about the problem. They were wrong about whether a solution existed. The Allied engineers who designed the Mulberry harbors had to solve every one of these problems simultaneously. They had to build structures that could withstand 21-foot tidal changes and still function as working harbor infrastructure. They had to design components that could be towed through channel currents without breaking apart or losing their position. They had to create breakwaters that could shelter a working harbor from Atlantic storms on a coastline that had never had a port in the first place. And they had to do all of this at a speed that peacetime engineering considered essentially impossible. The solutions they came up with were, in retrospect, elegant. In conception, they required thinking about the problem in a way that conventional harbor engineering had never been required to do. Because conventional harbor engineering always began with a fixed coast, a known geology, an established water depth, and years to work with. The Mulberry engineers had none of those things. They had 8 months, an enemy coastline they had never visited, and the English Channel. The Mulberry Harbor was not a single structure, it was a system, a collection of components, each solving a specific problem, designed to work together in a way that collectively produced something that functioned as a working port. Understanding the system requires understanding each component and why it existed. The first and most fundamental component was the breakwater. Everything else in the harbor depended on the breakwater working. Without shelter from channel waves and currents, no unloading operation could function reliably. Without calm water inside the harbor, pier heads would be battered, vessels would be unable to approach safely, and the entire logistical operation would be at the mercy of weather. The Allied engineers designed 2 types of breakwater. The simpler type, called a gooseberry, consisted of old ships deliberately sunk in a line, stem to stern, close enough together that their hulls created a sheltered area in their lee where small craft and landing vessels could operate in reasonable weather. 5 gooseberries were planned for the Normandy operation, less capable than the full Mulberry but faster to deploy and using vessels that were already at the end of their useful lives. The second type was the Phoenix, and the Phoenix was where the engineering ambition of the Mulberry project reached its most astonishing expression. A Phoenix caisson was a reinforced concrete box, not a small box. Each Phoenix was 60 feet high, as tall as a 6-story building, 200 feet long, a city block, 60 feet wide. It displaced 6,000 tons, the same as a Liberty ship. It was made of enough steel and concrete that its construction represented a significant industrial undertaking in its own right. What made the Phoenix remarkable was what it was designed to do. It was hollow, divided into watertight compartments. In that state it floated, a 6,000-ton concrete structure that could be moved across the English Channel under tow. When it reached its designated position off the Normandy coast, sea cocks were opened and the compartments flooded. The Phoenix sank to the sea floor, where it stayed permanently, its top still protruding 10 feet above the water surface at high tide, forming a solid wall against channel waves. 100 Phoenix caissons were built, placed end-to-end in 2 loam lines, one for the American sector and one for the British. They would form breakwaters of 2 miles each, 20,000 feet of combined wave barrier, sunk on the sea floor 1 mile offshore in 30 feet of water, creating a sheltered harbor behind them large enough to accommodate 7 Liberty ships simultaneously, with room for countless smaller vessels alongside. Building 100 structures of this size in 8 months required 20,000 British workers and a kind of industrial mobilization that the British economy, by 1943, had become capable of sustaining, but that would have been considered extraordinary in peacetime. The concrete alone represented a substantial fraction of Britain's construction material capacity. The engineering drawings were classified. The workers building them were not fully informed of what they were constructing or why. The Phoenixes sat on the sea floor off the English coast at Selsey Bill until they were needed, unseen from the air, looking from any reasonable distance like nothing more than underwater geological features. But the breakwater was only the outer shell of the harbor. Inside it, you still needed a way to get cargo from ship to shore, and that was where the tidal problem reasserted itself with full force. A conventional pier is fixed. Its deck is at a specific height. In a harbor with 21 feet of tidal variation, a fixed pier that was usable at high tide would be unreachable at low tide. The solution was the Lobnitz pier head, a structure that moved with the tide. The Lobnitz pier head looked, to those who saw it like a small factory built on a steel barge. 4 square towers at each corner, resembling industrial chimneys with massive steel legs that ran down through the structure and extended below the waterline, anchored to the seafloor. Inside the hull, complex machinery controlled the pierhead's vertical position. As the tide rose, the pierhead rose with it. As the tide fell, it descended. Its deck remained at a constant height above the sea surface regardless of whether the tide was at high or low water. An LST approaching to unload would always find the pierhead at the right height. The ramp would always reach, connecting the Lobnitz pierhead's position inside the breakwater half a mile offshore to the beach itself, or the floating roadways, enormous steel truss sections that the Mulberry engineers called whales, each section floating on pontoons and connected to the next to form bridges up to 3,000 feet long running from the beak out to the pierheads. These bridges rose and fell with the tide along with the Lobnitz units, maintaining a consistent grade that vehicles could actually drive on. Tanks, artillery, trucks loaded with ammunition, all of them rolled along floating bridges across half a mile of sea from the pierheads to the beach, continuously, around the clock. The full system, Phoenix breakwaters, gooseberry ships, Lobnitz pierheads, whale floating roadways, when assembled off the Normandy coast formed a structure roughly equivalent in handling capacity to the port of Dover. Not as large, not as capable, but functional, real, a working harbor where 10 days before there had been only open beach. 600 sections of roadway, 100 Phoenix caissons, more than 100 tubs to move them, all of it assembled in 8 months and then towed across the English Channel to be assembled on an enemy coastline under fire. When Eisenhower visited Selzy Bill and saw the components sitting on the seafloor waiting for the invasion, he later wrote that their immense size astonished him. Nevertheless, he said he was confident they would work. That confidence was not casual. It was the confidence of a man who had been briefed on what the engineers had built and understood, perhaps better than anyone else in the Allied command, how much everything that came after D-Day depended on those concrete boxes and floating bridges working exactly as designed. Moving the Mulberry components from England to Normandy was, in its own right, one of the most complex naval operations of the war, not because of enemy action, though that was a real concern, but because of the sheer physical difficulty of moving structures of that size through the English Channel at any speed at all. The Phoenix caissons could be towed at approximately 3 to 4 knots. That is roughly the speed of a brisk walk. At that speed, crossing the 100 miles of channel between the English coast and the Normandy beaches took the better part of 2 days. 2 days of towing a 6,000-ton concrete structure through channel currents and tides, with tugs powerful enough to maintain direction but not powerful enough to overcome the full force of channel weather if conditions deteriorated significantly. The timing was everything. The operation had to begin with enough weather window to get the components across before conditions could threaten the tow. Once a Phoenix was in the water and being moved, it could not simply be stopped. You could not anchor a 6,000-ton concrete structure in open channel water and expect the anchor to hold in any kind of sea. If you started the tow, you had to finish it. The crossing began in the days immediately following D-Day, as the fighting on the beaches continued. Tugs left from multiple English ports, towing their enormous cargo through waters still contested by German naval forces and aircraft, navigating by night with reduced lighting, managing the currents that tried to push the tows off course, and working under the continuous pressure of an operational timeline that left no room for significant delay. The Phoenix caissons arrived in sequence. As each one reached its designated position, it was scuttled, the sea cocks opened, the compartments flooded, and it sank exactly where the engineers intended it to go. Then the next one arrived and took its place. Then the next. The breakwater line built itself piece by piece across the sea floor, one concrete box at a time, each one adding to the shelter that would make a harbor inside it functional. Alongside the Phoenix operation, the Gooseberry ships, older vessels no longer fit for combat, were sailed to their positions and deliberately sunk in their designated lines. This is simpler than the Phoenix tow, but still required careful positioning to ensure the shelter they created was in the right place and oriented correctly relative to the prevailing weather and wave patterns. The floating whale roadway sections were towed in separately and assembled progressively as the pier heads were positioned and the Phoenix breakwater took shape. The entire operation required coordinating hundreds of vessels, dozens of specialist engineering units, and a logistical pipeline moving components across the channel continuously for weeks. ID+10, June 16, 1944. The first Mulberry Harbor was sufficiently complete to operate. An LSD nosed up to the earth completed the runway, dropped its bowwhip onto the Lobnitz head, and 10 vehicles began rolling short off the floating whale roadway. In 2 days of initial operation, 24,000 tons of supplies and ammunition came ashore across the 2 Mulberry harbors. The German General Staff, which had categorically concluded that sustaining a major invasion at Normandy was logistically impossible, was being proved wrong in the most direct way possible. The harbor they had said could not exist was operating. And then the storm came. June 19, 1944, D+13. The English Channel does what the English Channel does. A gale of unusual severity moves in from the northwest. Wind speeds reach storm force. Swells build to heights that make the channel effectively impassable for the landing craft and small vessels that had been sustaining operations on the beaches. The kind of weather that had stopped invaders of England for centuries descends on the most critical logistics operation in the history of warfare. For 3 days, the storm hammers the Normandy coast. Landing craft are driven against the pier heads by wind and wave. The whale roadway sections, designed to flex with the sea, are pushed beyond the range of their engineering tolerances and begin to break apart. Sections tear free from their moorings and crash into each other and into the Phoenix caissons. The Loveness pier heads, the legs anchored to the seafloor, hold, but the roadways connecting them to the beach begin to disintegrate. By June 22nd, when the storm finally eases, the damage is catastrophic. Mulberry A, the American harbor off Omaha Beach, is destroyed. Not damaged, destroyed. The floating roadways are a mass of twisted wreckage. Sections of the pier head infrastructure have been driven against the Phoenix breakwater and damaged both. 800 vessels of various sizes are beached or wrecked along the American sector of the coast. The harbor that took 8 months to build and 2 weeks to tow across the channel and assemble under fire has been reduced in 3 days to something that can no longer function as a harbor. Think about what that means for a moment. The most important logistical operation in the Allied war effort, the infrastructure that everything else, the advance inland, the armored breakout, the liberation of France, depends on for its supply. But, in 72 hours, by weather. The German General Staff, if they had fully understood what had happened, would have recognized that the Channel had achieved in 3 days what their coastal defenses had failed to achieve on June 6. The supply line of the Allied invasion had been severed, not by enemy action, by the sea itself. But the story does not end there, because the destruction of Mulberry forced a set of decisions and adaptations that revealed something important about how the Allied logistical operation actually worked, and why it was more resilient than the storm damage alone suggested. The British Mulberry B off Gold Beach at Arromanches was also severely damaged but not beyond repair. The Phoenix breakwater had held. The pier head structure had survived with repairable damage. The floating roadway sections were damaged but salvageable in part. Allied engineers immediately began assessing what could be saved and what could be rebuilt. The decision was made to abandon Mulberry A entirely. Its salvageable components, pier head sections, roadway elements, anything that could be removed from the wreckage, were towed to Arromanches and incorporated into the British harbor. What remained of the American installation was left where the storm had put it. Simultaneously, the American sector switched to a different approach. Rather than wait for harbor reconstruction, the Americans drove their LSDs directly onto the open beach at low tide, unloaded them as quickly as possible before the tide came in, and refloated them as the water returned. The technique was not sophisticated. It was not efficient by the standards of a working harbor, but it worked. On June 23rd, with the storm barely finished and Mulberry still a field of wreckage, the Americans landed 16,400 tons of supplies on the open beaches. The German calculation that a sustained invasion supply operation on the Normandy coast was impossible without a working port was being proved wrong not by the Mulberry harbors alone, but by the combination of Mulberry engineering and American logistical improvisation. When the engineered solution failed, the Americans found a raw solution. When the raw solution was eventually exhausted, the engineered solution at Arromanches was theirs backup. The British Mulberry B at Arromanches was restored to operation within weeks, supplemented by salvaged components from the destroyed American harbor. It would operate for 10 months, from the D-Day landing until March 1945, handling supplies, equipment, and reinforcements that sustained the Allied campaign across France and into Germany. The storm that destroyed Mulberry had come closer to derailing the Normandy campaign than any German military action between June 6 and the breakout in late July. Eisenhower later wrote about it with the directness of a man who understood how close the margin had been. The weather had done what the German coastal defenses and the Wehrmacht had failed to do. It had temporarily stopped the Allied supply line. The fact that the supply line started anyway, through improvisation, through the survival of Mulberry B, through the sheer logistical momentum of an Allied war machine that had been building toward this moment for 2 years, is the real story of what the Mulberry harbors were. Not just the engineering, the resilience. The numbers that the Mulberry Harbor at Arromanches eventually produced are, in the context of military logistics, extraordinary, and I think they are worth sitting with specifically rather than as abstractions, because they are what translated the engineering achievement into the military outcome. In the first week of full operation before the storm, the two Mulberry Harbors together had already moved 24,000 tons of supplies in 2 days of operation. After the storm, with only Mulberry B functional but now augmented by components salvaged from the destroyed American harbor, the throughput built steadily through the summer of 1944. By August 1, 1944, 7 weeks after D-Day, the Allied armies ashore in Normandy had sufficient strength, equipment, and ammunition to break out of the beachhead. Operation Cobra, the American armor breakout near St. Lo, punched through the German defensive line on July 25. General Patton's Third Army poured through the gap, swept south and then east, and the liberation of France began to unfold with a speed that surprised even the optimistic Allied planners. That breakout was possible because of what had been moving across the floating bridges and through the harbor at Arromanches for the previous 7 weeks. Hence, artillery, ammunition, fuel, replacement troops, all of it arriving continuously, building up the logistical reserve that made a major armored offensive sustainable rather than a one-time push that would run out of fuel before it reached its objectives. Every reinforced Allied division needed 600 to 700 tons of supply per day. By the time of the Cobra breakout, the Allies had enough divisions ashore to require many thousands of tons of supply daily just to maintain current operations, and many more thousands of tons to sustain the offensive operations they were about to launch. The Arromanches harbor and the beach supply operations together were producing those numbers, not comfortably, not without stress on the supply chain, but producing them. What was crossing the water in those weeks was the physical substance of a military decision. Every ton of ammunition that arrived was a future firefight that American or British or Canadian soldiers could win rather than lose for want of shells. Every tank that rolled down a whale roadway was an armored engagement that might go differently than it would have without that tank. Every gallon of fuel was a mile of advance that might not have happened if the fuel had not arrived. Logistics is often treated in historical writing as the unglamorous background to the dramatic foreground of combat. But logistics is the grammar of military operations. Without it, the most courageous soldiers and the most brilliant commanders produce battles they cannot sustain and offensives that run out of momentum before they reach their objectives. The Normandy campaign demonstrated this as clearly as any other of their victory, because the margin between if its supply was close enough, especially in this first one of it in June, that the difference between the two of them was visible. The Germans, who had correctly identified port capacity as the critical vulnerability of any Allied invasion of northern France, had built their entire defensive strategy around denying the Allies that capacity. They had demolished Cherbourg. They had fortified the major channel ports. They had bet that the invasion could not be sustained without conventional port infrastructure. They had not built their strategy around the possibility that the Allies would bring the port infrastructure with them. That possibility had not been in the calculation. It was not in any doctrine. It had not appeared in any pre-war military engineering literature as a practical option. It had been laughed at when it was first proposed. And so the Germans lost the logistical bet that underpinned their entire defensive concept. They lost it because 20,000 British workers that 8 months building heavy bases had floated, and because naval engineers designed a spearhead that moved at its side, and because someone in 1942 looked at the problem of invading France without port, they decided that the answer is to build a port and bring it along. There is a version of the Mulberry Harbor story that focuses almost entirely on the engineering, the phoenixes, the Lobnitz pier heads, the whale roadways, the technical specifications, and the construction timeline. That version is important and necessary, but it risks leaving out the human element that makes the story genuinely extraordinary. The Mulberry Harbors did not spring into existence from a planning document. They grew from a proposal that was initially dismissed through a development process that required continuous advocacy against institutional skepticism into an operational reality that worked well enough to matter and broke down in ways that had to be overcome in real time under operational pressure. Lord Mountbatten, who proposed the idea in 1942 and absorbed the laughter in that conference room, was not an engineer. He was a naval officer with a gift for unconventional thinking and enough standing in the Allied command structure to put an unconventional idea in front of the people who had the authority to act on it. When the idea was laughed at, he did not withdraw it. He continued to advocate for it in subsequent planning discussions, eventually persuading enough senior figures that a feasibility study was worth commissioning. The engineers who took the feasibility study and turned it into a construction program were working in conditions that would have been unusual in peacetime and were genuinely extreme in wartime. The design of the Phoenix caissons required solving engineering problems that had no established solutions. How do you build a 6,000-ton concrete structure that floats, can be towed 100 miles, and then sinks in exactly the right place and stays there permanently? How do you design a pier head that moves vertically with a 21-foot tidal range while still being mechanically reliable enough to operate continuously under the stress of cargo handling? How do you build floating road sections that flex enough to handle channel swells without breaking at their connection points? Each of these was a genuine engineering challenge. Each was solved under time pressure that made the standard iterative process of engineering development, design, test, refine, test again, essentially impossible. You could not build a prototype Phoenix case and tow it across the channel, sink it, and then redesign based on what you learned before. You had to build the rest. The construction timeline meant that the design had to be essentially right the first time, at scale, in conditions that no engineer had previously worked in. The workers who built the components, 20,000 of them, many working on structures whose purpose they did not fully understand, were doing work that was physically demanding, technically complex, and conducted under the security restrictions that made it impossible to get them to them by the strange concrete boxes they were building mattered or what they were going to become. They built them anyway, with the competence and commitment of a workforce that had been producing extraordinary things since 1940 out of necessity. And then there were the sailors and engineers who moved the components across the channel and assembled them under fire on the Normandy coast. Towing a Phoenix case in the channel curtains at 3 while German aircraft might appear overhead and German U-boats might be operating in the same waters required a combination of seamanship, navigation skill, and the particular courage that comes from operating in an exposed and vulnerable position without the ability to maneuver quickly or fight back effectively. Many of the people who made the Mulberry Harbor's work are not named in the historical record. The workers at Chelsea Bill, the tug crews crossing the channel, the engineering officers managing the assembly of components on the Normandy coast while the battle for the beachhead continued around them, the logistics specialists who improvised around the destruction of Mulberry after the storm and kept the supply line moving through improvisation while the engineers rebuilt what they could. History tends to attribute great achievements to the people whose names appear in the planning documents and the post-war memoirs. Eisenhower planned the invasion. Mountbatten proposed the harbor. Montgomery commanded the ground forces. These attributions are not wrong, but they are incomplete. The Mulberry Harbors were not built by the people who appear in the history books. They were built by 20,000 workers whose names are not in most accounts of the Normandy campaign and whose contribution to the liberation of Europe was as real as any general's. There is a sentence in the historical record of the Mulberry Harbor operation that I find genuinely striking. It appears in various forms in the post-war assessments of German military planning for the defense of Normandy. The German General Staff, it notes, fervently believed that no invasion could possibly be staged successfully at Normandy. They were wrong, but they were not stupidly wrong. They were wrong in the way that rational people are wrong when they apply correct reasoning to an incomplete model of reality. They had identified the port dependency correctly. They had correctly calculated that a sustained invasion required port infrastructure beyond what open beaches could provide. They had correctly concluded that the Normandy coast, without a major port accessible to the invading forces, could not support a successful invasion. Every step in that reasoning was sound. The conclusion was wrong because the premise was wrong. The premise was that the Allies could not bring port infrastructure with them. That premise had never been tested before. It was not an unreasonable assumption. Nothing in the history of military operations up to 1944 had suggested it was possible. The German planners were applying the doctrine of every army and navy that had ever studied the problem of amphibious supply. They simply did not know that the Allies had solved the problem in a way that fell entirely outside the scope of existing doctrine. This is, in a broader sense, the story of the entire Allied war effort from 1942 onward. The Allied What the Allies could do was solve problems that the German system had not anticipated. The dog drag that defeated German tracking dogs. The measle map that turned Aachen into a numbered grid. The hedgerow cutter that a sergeant from New Jersey welded together from scrap iron. The Phoenix caissons that 20,000 British workers built in 8 months. Again and again, the Allied advantage was not tactical genius or superior individual fighting skill. It was industrial and engineering creativity applied to problems the German doctrine had declared unsolvable. The Germans were very good at fighting the war they had prepared for. The Allies kept changing what kind of war it was. The Mulberry Harbor is the logistical expression of that pattern. The Germans had correctly identified the logistical constraint that made a Normandy invasion inadvisable. The Allies responded by engineering their way around the constraint, not by finding a port somewhere else, not by changing the invasion site, by building the missing infrastructure and bringing it across the channel in pieces. The German response to learning that the Allies had artificial harbor infrastructure was, by the accounts that survive, something close to disbelief. This was not a tactic they had wargained. It was not a contingency they had planned around. The elaborate coastal defenses of the Atlantic Wall had been designed with the assumption that sustaining an invasion without a port was impossible. The moment that assumption was falsified by a field of concrete caissons sitting on the Normandy sea floor, the entire strategic logic of the German defensive position in France began to unravel. They could fight for every village. They could destroy Cherbourg before surrendering it. They could counterattack at Mortagne. They could move armor to the threatened sectors and contest every yard of advance. All of those things they did, and all of them delayed the Allied advance and cost lives on both sides. But none of them could address the fundamental problem that the Allied supply line was working, and a supply line that works eventually wins. The Mulberry Harbor at Arromanches operated for 10 months. From June 1944 to March 1945, it handled approximately 2.5 million men, 500,000 vehicles, and 4 million tons of supplies. Those numbers represent the material substance of the liberation of Western Europe. Every soldier who crossed France, every tank that drove toward Germany, every gallon of fuel, every artillery shell, every medical supply that kept the Allied armies fighting and advancing through the summer and autumn and winter of 1944 and into 1945. Some of it came through the ports that were eventually restored and reopened, Cherbourg, Antwerp, others. Some of it came across open beaches, but the harbor at Arromanches was the infrastructure that made the sustained Allied offensive possible in the critical early months when the beaches were the only supply point and the ports were still in German hands or being laboriously rebuilt after German demolition. The Phoenix caissons are still there. If you go to Arromanches today, a small town on the Normandy coast that draws visitors precisely because of what happened there in 1944, you can see them from the beach. The concrete boxes that were built in England in 1943, towed across the channel, and sunk on the sea floor now protrude above the water at low tide as the most extraordinary monuments to logistical achievement in military history. They are not dramatic. They do not look heroic. They look like what they are. Large concrete objects sitting in the sea, but they have been there for 80 years and they are still recognizable as the thing they were built to be. There is a museum in Arromanches dedicated to the Mulberry Harbor. It sits at the edge of the beach where the floating roadways once ran out to the pier heads, and from its windows you can look at the remnants of the Phoenix breakwater in the sea. The museum is not large. It does not attract the crowds that Omaha Beach draws, or the Normandy American Cemetery, or the sites associated with the parachute landings and the direct infantry assaults. That relative obscurity is appropriate in one sense and deeply unfortunate in another. Appropriate because logistics is always less dramatic than combat. The men who assembled the Mulberry Harbor components under fire on the Normandy coast were not storming a beach. They were doing technical work that looked, from the outside, like construction rather than fighting. The courage it required was real, but not the kind that generates the photographs and the citations that become the public memory of a battle. Unfortunate because the Mulberry Harbor is the reason the men who stormed the beaches survived in sufficient numbers to do the rest of the job. The harbor is the reason the supply line held. The supply line holding is the reason the Allied armies could sustain the offensive operations that drove the Wehrmacht back across France and into Germany. Take the harbor out of the chain and the chain breaks. Not immediately, not on June 6th itself, but in the weeks that followed, as the logistical demands of a sustained offensive in France began to exceed what open beach operations could provide. The harbor was the difference between a supply line that worked and one that did not. The German General Staff had concluded that no invasion could be staged successfully at Normandy because no adequate port was available. They were right about the requirement. They were wrong about whether it could be met. And the reason they were wrong is that someone in a British conference room in 1942 proposed an idea that was greeted with hoots and jeers, and the idea was right. Lord Mountbatten did not build the Phoenix caissons. The 20,000 workers at Selzyville did that. Mountbatten proposed the concept and kept proposing it until the right people took it seriously. The engineers designed the components. The workers built them. The tub crews crossed the channel with them. The naval and engineering units assembled them on the Normandy coast under fire. Eisenhower made the decision to include them in the Overlord plan when he could have concluded they were too uncertain and too complex for an operation that already had enough complexity to manage. All of those people, named and unnamed, are part of the same story. The story of how an idea that was laughed at in 1942 became the logistical foundation of the liberation of Europe in 1944. If you have ever stood on the beach at Arromanches and looked at those concrete shapes in the water and wondered what they were and why they were there, now you know. And if you find it history, the kind that isn't about no if the kind that is usually there's no workers the names are not of alignment. If that is the kind of history that he thinks they know what to do. The Germans said it was impossible to sustain a landing at Normandy without a port. The Allies agreed, so they built one, put it on boats, and sailed it across the channel.